Here we go. Okay, let's orient ourselves. If I read the schedule correctly, next week is spring break. Everybody think the same thing? Okay. So we won't be meeting next week. Week after, if we get finished with all the solutions today, Chapter 8, then we can start review next week. And we'll also have a week after that before the exam. The exam's on the 19th of April. And I never move the exam up. I can postpone it, but I never move it up unless the whole class wants it earlier. So if the whole class says, okay, then we could have it a week early, but that's just an option that you could consider if you feel ready. If you don't feel ready, we'll keep it on schedule. And that exam will cover only Chapter 7 and 8. Gases, liquids, and solids, and solutions. Let's see. But our lab, when we come back, our lab will be molar mass by freezing point depression. So what I may do, that would be good. If we can get through Chapter 8 today, then we can use a large chunk of our lecture to discuss freezing point depression and the mechanics of the lab. That would work out. Okay, let's see if I can find one of these that works. Not bad. You can see it on the video. Have y'all had any trouble accessing the videos on Blackboard? They come up okay? Good. I was wondering there for a while because I had uploaded them as private. And one time I tried to go in and access them, and I couldn't. Because when they're private, you have to say who has access to them by their emails. So I changed them all to public. Okay, solutions. So remember what a solution was. We talked about different types of mixtures at the very beginning of the year. And a solution is a homogeneous mixture. That just means any place you look in the mixture, you're going to find the same relative amounts of all of the components. And in fact, solution is synonymous with a homogeneous mixture. We can have, what types of solutions can we have? We normally think of solids dissolved in liquids, like salt in water or sugar in water. But solutions can be any kind of mixture. You can have one phase mixed in another as long as it's completely homogeneous. We're breathing a solution now. Solution primarily nitrogen and oxygen. If you wear a ring of any kind, it's probably a solution. Particularly if it's gold. We rarely have 24 karat gold on our fingers. It's too soft. It won't last very long. So mine's 14 karat, which is 14 divided by 24, whatever that fraction of gold is. And the rest of it is base metals. Sometimes a little silver, but mostly copper. They put copper in there because it comes out the same color as gold if you want yellow gold. If you want white gold, then they put something else in it that modifies it. But it's still a solution with a special name. We call it an alloy. Okay, we're going to talk about solutions in particular, and we're really going to focus primarily on aqueous solutions because that's where most of the interesting reactions occur for people in the life sciences or in the laboratory sciences. Non-aqueous solutions are important, but they're just not common. Okay, so there's our homogeneous mixture, and we did talk about that at the very beginning, didn't we?
Yeah, I think you accidentally went back after this one, because I think I don't know if you just went over this or not, but
Did I go into this already?
pretty good. I think so.
Oh,
I think you went back to the chapter outline.
okay. Because I thought I had only gone through chapter 7. Did we jump into chapter 8 a little bit?
Oh, no, I thought you meant, did you go back on the slide? I'm sorry. I thought you already explained this slide because you started talking about the homogeneous mixture.
Yes, yes. Because I thought we had covered some of those characteristics in one of the earlier chapters.
It might be.
I think we talked about it a little bit, but we didn't fully discuss.
Yeah, like pure substances, elements of compounds, things like that. Okay, well, it won't hurt to hit it again.
I think we did a lab on mixture.
Yes, that's true.
So that might be where you went over it already. Yeah.
Okay. So we can have various types of mixtures. I mentioned solids dissolved in liquid. No, I guess we didn't go over this. Okay, I better introduce it properly now. A homogeneous mixture is another name for a solution, and it can be almost anything. Solids and liquids, you will normally think of sugar water would be an example of that. Liquid and liquid, you know, any kind of alcoholic beverage, you mix ethanol with water and other compounds. Gases can be dissolved in liquids. You know, when you open a pop bottle, that's why it goes pop, because some of the gas in it wants to escape. But as long as you got the lid on there, it stays in solution. The air we breathe, alloys, there are various other kinds, but those are some examples. Now, the term solvent and solute. The solvent is, at least at the very beginning when you make a solution, the solvent is the major component. So if you're going to dissolve a little bit of salt in a lot of water, the water is the solvent, and the salt is the solute. Now, if you try that with sugar, you start off with a half gallon of sugar, water, excuse me, and you're going to make a sugar solution for your hummingbirds, then you usually do 50-50. Same amount of sugar and same amount of water. But when you start out with water, and you start putting sugar in it. So the sugar becomes the solute, the water is the solvent. The funny thing about sugar is you can eventually end up with more sugar in the solution than you have water. But in that case, the convention is you revert to where you started. You started with more water, so water continues to be the solvent, even though eventually it's the minor component. Okay, so here's an example. We're going to put, there's a spatula with some solid that goes into solution, and eventually we get a uniform mixture, a homogeneous mixture, and another indicator that you have a solution is you can see through it. Now that wouldn't be the case with an alloy, but with an aqueous solution, you can see through it. And another way to tell if you have a solution is to take a light and shine it from the side through your solution. And if it is a solution, the light beam will go through and come out the other side. You can shine it on your hand, but you can't see it in the solution. Right? There's no diffraction of your light beam as it goes through. If you can see your light beam going through there, then you don't have a solution. You may have a suspension, but it's not a solution. That's known as the Tyndall Effect. We use that sometimes when we're doing titrations where a precipitate is forming, and you want to add a little bit of one reagent into another and know exactly when the point of precipitation starts. And we use the Tyndall Effect. You shine your light through there and you add a little bit and you mix it. As soon as you see that Tyndall Effect, the scattering of light, you know that the precipitate has started. That increases the sensitivity of your test. Okay. Now, solutions can contain more than one component. But only one of them is the solvent. The rest of them are the solutes. So you can have 2 or more solutes, but you can only have one solvent. The composition can change if you add more solute or if you add more solvent. That will change the percentage composition of each of your solutes in solution. But once the solution is reestablished, after you add more of one of the components, at that point, the composition is uniform throughout. Right? It can change, you can change it, but it's still uniform if it is a solution. Properties of the solution can change depending on how much you have. You'll notice that if you start to make that sugar water for your hummingbirds, it starts off, you stir it, and the water splashes around like normal. But as you get more and more and more sugar in there, it gets a little thicker or viscous. So the composition of the solution will change its physical properties. So in what form do the solutes, the substances dissolved, what form do they take when you put them in solution? Well, it depends on what they are. If they're molecular, such as glucose, and of course table sugar would be sucrose, those are molecular. So when they go into solution, they maintain the structure of that molecule. They don't break apart. Okay? If you put table salt in solution, once it goes into solution, it breaks up into its ions. Okay? That's why it goes into solution. It will not stay solid, at least in the beginning. Sometimes, instead of molecular, it could be atomic. Right? So you can dissolve things like noble gases. Right? You could put, say, neon. It might be a gas, but you put it in solution, and you get some of it dissolved in solution. Of course, it's not going to break apart because it's atomic. And then there are other compounds, when they break apart, instead of producing ions, they do produce atoms, but they're not very common, so we're not going to discuss them. Now, another characteristic of solutions is you can separate the solute from the solvent by purely physical means. That is, you don't have to break any bonds to do that. So if we have sugar water or salt water, all you have to do to get these solutes back out is just heat the water, heat the solution. Water evaporates and leaves these behind. That's purely a physical process where you just boil the water away, change the water's phase from liquid to gas, and you get these back. Okay. So which one is in this mixture, 80 milliliters of water and 20 milliliters of alcohol, I assume they mean ethanol. Which one is the solvent? Which one's the solute? Which one's the major component? That's the solvent. It's water, isn't it? Water's the major component, so it's the solvent. And alcohol is the solute. Okay. Another term that's common with solutions is solubility. Another way of saying that is the ability to dissolve. What we mean is, how much of the solute can we put in the solvent? Because it is possible to fill it up, and you get, at some point, the solvent won't hold anymore. There's no more room. We'll have to talk about the particulars of that later. But when you reach that point, we would say the solution is saturated. It has reached its maximum solubility. You can do that with sugar in water. You can do it with salt in water. I've made saturated solutions of salt water for one of my labs. The conditions have to be constant. In other words, if it's a solid in a liquid, usually the only condition you have to deal with is temperature. And most solids, when they go into solution, will increase solubility as you increase the temperature. There are a few exceptions, but most of them, when you increase the temperature, you can put more solute in your solvent. So that's another way to remove, by physical processes, part of the solute from your solution. If you're at saturation, you've got all the solute you can get in your solution at this temperature, just cool it down. And it won't hold as much. And some of it will start dropping out of solution. Okay, it'll precipitate out. Then you can filter it. Like I said before, most solids become more soluble. And since we're talking about aqueous solutions primarily, but water is our most common solvent. So the solubility increases with temperature. However, for gases, as temperature increases, solubility decreases. Now, there are exceptions here too, but for most cases, when you increase the temperature, you decrease the solubility of gas. So you notice when you put water on the stove to boil, before it actually starts rolling its boiling, you'll see little bubbles form, little gas bubbles form. They're usually on the sides against the walls of your pot. Those, as you heat this water up, those are gases that are dissolved in water. As you heat it up, those gases come out of solution because their solubility decreases. So they have no place to go except out. Okay, so here's how we express. Usually when you look up in a reference manual, the solubility of a compound, and it's usually referenced to water, it will give you a temperature, and it will give you the units of measure as the grams of solute per 100 grams of water. So that just means if you have 100 grams of water to start with, then you should be able to dissolve that much lead-2 bromide at 50 degrees centigrade in 100 grams of water. Okay? And it looks like as the temperature increases, we get increased solubility. Let's see if there's one in here that goes the wrong other direction. Okay, there we go. No, all of these are more soluble as the temperature increases. There's this big thick book called the CRC Manual. CRC stands for Chemical Rubber Company. They started off oh my goodness, over 100 years ago. Oh, more than that. Almost 200 years now. Started with a little manual, it's about this big, and stuff like that. I've got an old version, and it's leather bound, and it's got the gold around the edges of the pages. Now the book is about that wide, about this big, about that thick, with physical and chemical information in it. And this is some of the stuff that you'll find in that book. It's a good reference manual. Okay, here's an exception. Calcium acetate. Okay, so if you remember your polyatomic ions, acetate is C2H3O2 minus, polyatomic ion. And if you combine with the calcium, so this is 1 minus and this is 2 plus, so you have to do this. So that compound, when we put it in solution, is more soluble as the temperature decreases. That's not common, but it does happen. And there's some other acetate compounds that do the same thing. Ammonium acetate will do that. I think even sodium acetate will do that too. So what about the solubility of, we talked about temperature effect. What about pressure? Where would pressure be a consideration for solubility? When you're trying to dissolve gases, right? When you try to put a gas in solution, say in aqueous solution, you need to consider pressure. Right? So as long as your pop bottle is sealed, the pressure inside is at a certain level, keeping that CO2, carbon dioxide, in solution. But when you crack the top, you release that pressure. And usually, some of the CO2 comes out of solution. You know, if you don't shake it up beforehand, then not much. Or, I'll give you this one in a minute. If you shake it up before you open it, right? If you drop your 2-liter bottle on the floor and you don't wait a while, then you pop it open and it goes psh, everywhere. So the pressure over the surface of the liquid is a factor in determining solubility of a gas in the liquid. Okay? Temperature also has an effect. Before we talked about temperature, gases are usually more soluble with lower temperature. So that's why I take my 2-liter bottles of pop, and before I open them up the first time, I stick them in the refrigerator for a couple hours, get them cold. Then when you open them up, you don't lose all that carbon dioxide. That's why I hate to go picnics, because picnics, they usually have the CO2 sitting out on the bench, 90-degree temperature in the middle of the summer. And within a few minutes after I open the bottle, all the CO2 is gone. Okay. Okay, what's the effect of pressure? Well, I talked about gases, but just to make a point, pressure has very little effect on the solubility of solids or liquids in water. Right? Because, well, pressure has very little effect on solids and liquids to begin with. Right? They're incompressible. You can't squeeze them. Gases, you can. So the effect of pressure on gases is significant. Now we can quantify this. Henry, I think he was English, came up with this law. It just says, in words first, the amount of gas that will dissolve in a liquid at any given temperature is proportional to the pressure of the gas above the liquid. So you increase the pressure, you get a proportional amount increase of gas dissolved in the liquid. So how would we do that? Well, one way we can do it is is get a marker that works. So we have this vessel. Remember when we were talking about gases before, we had a piston. So you can push down on it. And you have a trapped gas. But only this time, instead of just the gas in there, for our gas law discussion, we have a liquid in the bottom. So we have gas up here, and let's say we have water down here. So as you press on that, you increase the pressure on that gas, more of it will go into solution. Okay? And it's proportional. So the concentration of the gas in solution increases, concentration in solution increases with pressure. So we increase the pressure, we get an increase in concentration, and there's a constant. Right. And this constant is characteristic of the system, the gas and the liquid together. And this, remember Dalton's law of partial pressures. If you have a mixture of gases in here, you can calculate the solubility of each one of the gases in there as long as you know its partial pressure. So if we have air in here, we know that the partial pressure of, if you have 1 atmosphere, let's say we're starting at 1 atmosphere pressure, then nitrogen is 79%. So its partial pressure is going to be 0.79 atmospheres. And the partial pressure of oxygen is going to be 0.2 atmospheres. So you can determine the solubility for each one as long as you know the partial pressure. Okay. If it's a pure gas, then you only need to measure the exact pressure of the total. Okay, back to solubility. We might talk about Henry's law again, we might not. And that all depends on whether you have, did I assign you any problems to do with Henry's law? Then we can talk about that when we do review as well. So, the solubility of a solute in a solvent, we have different terms that can be associated with that. When you reach the maximum amount of solute that will dissolve in a solvent at a given temperature, and if it's a gas, pressure, then that point where you reach your maximum is called saturated. So the solution is saturated. And that's our reference point. So if it's less than that point, we say it's unsaturated. If it's more than that point, which can happen, sometimes you can get more solute dissolved in there than you expect. We say that's supersaturated. Supersaturated solutions are very unstable. So if you have a supersaturated solution, usually all you have to do is disturb it. And it will immediately, the excess will come out of solution. The best way to do that is to find out what your saturation point is and put more solute in there than you need, and heat it up. Get it all to dissolve, and then set it on the bench and where it's not going to be disturbed. Just let it sit. And as it cools down to room temperature, if you're lucky and you haven't put too much more, then it'll stay in solution as long as you don't disturb it. But all you have to do is just pick it up and say, just like that, and it just all drops out. That's an understatement. They're very unstable. You can stir it that way, or a trick that
particularly organic chemists use, is if they want to cause a precipitation to start, they'll just reach into the flask with a sharp, a metal object and scratch the inside of the container. Then those spikes, the little microscopic projections that they leave behind when they scratch the glass, is sufficient to start the precipitation process.
Unsaturated solutions, they're below the maximum. And most solutions are in that region. Saturated solutions have their uses, but they're very specific. So generally what you'll do is if you prepare a solution, it will be unsaturated on purpose. Another way to describe your solution is whether it's concentrated or dilute. And these are relative terms. A concentrated solution has a lot of solute relative to the amount that can reach saturation. So if a large percentage of the saturation amount is in solution, then you say it's concentrated. If only a very small amount of solute is in solution relative to its saturation point, then it's called dilute. A dilute solution might be 0.01 molar hydrochloric acid. That'd be a pH of 2. We haven't talked about pH yet, have we? That's later. Acids and bases. Concentrated solution of hydrochloric acid is readily available. I used to buy it this way, 37% hydrochloric acid. And you open the cap and it starts fuming. You know you've got concentrated hydrochloric if it starts fuming. So you deal with that one under a fume hood. Whereas a concentrated solution of a concentrated sulfuric acid is available at 98%. Extremely high concentration and hazardous. Now, I would say that sugar solution that you're going to put out for your hummingbirds, 50-50 mix, that would be concentrated. So this is a dilute solution. This is a concentrated solution. My guess is that you've got the same amount of that blue dye, or whatever chemical makes it blue, the same amount by mass in both beakers. Only in this one you have a lot of solvent, and this one you have just a little bit of solvent. So the concentration is much higher over here, because for every milliliter you have more of the solute than for every milliliter here. Okay, so we're going to talk about mostly aqueous solutions. If water is not the solvent, it's just non-aqueous. Okay, so we've discussed the increase in temperature decreases gas solubility in water. Okay. The conventional wisdom, or the widely accepted theory for how do solutes go into solution. 3 things happen. So you have your marker that doesn't work. You have your solute and your solvent. Okay? And you want to make a solution. It's not working well either. It's time to go into my pockets. Try this one. So what has to happen?
Well, see, this is a pure substance when you start. This is a pure substance when you start. So there are interactions between the atoms or molecules of each one of these within themselves. And before you can get them to interact with one another, you've got to break the bonds that hold these together. Right? So the attractions that hold this one to itself and this one to itself have to be broken. So that's step 1 and step 2. Break the intermolecular attractions for both of them. Okay, you pull them apart. In this case, we would say we're making them separate from one another so that they can interact with the solvent. And another way of saying breaking the bonds for the solvent is we're making holes. Make a place for these to go. Right? And these usually require an input of energy. To break those bonds. Okay, so you have to add energy here and here. Now, when you make the solution, you're going to, you have intermolecular forces, form bonds between solute and solvent. Okay. So when you have the solvent and the solute here, and you allow them to attract one another, their energy level is high here and low here when they form the bond. Right? So if the energy level is high here and low here, where does that energy go? Well, it gives it up. Usually it's heat. So the reason I say that is you've got to put energy in here, energy goes in here, but you get some of it back in this step. So this is the third step. When you form the bonds between solvent and solute, you get some of that energy back. Okay? So with the, we'll call this E1 plus E2, input energy here, here, and here to break those bonds apart. And then E3, you get some of that energy back. And that equals the overall change in energy. So the reason I put it that way is some solutions, anybody here work in a hospital setting? Okay, you know about hot packs and cold packs. Now they have the little plastic bags, and there's usually water, and then they have a little container inside that's separate from the water, and then you have to pop it or break it or something and mix it. Right? The hot packs get hot, and the cold packs get cold. That's an expression of the heat of solution. Right? So the hot packs are the ones where you put energy in here, but you get a whole lot of energy back during this step. You get more energy back here than you put in. So this one is the high one for a hot pack. A cold pack, you don't get as much back here. Right? If you get less energy back than you put in, then it's going to start feeling cold. Okay? That's the reason I hammered these individual points, so that we can understand why some solutions get cold and some solutions get hot. Okay, fast do things go into solution? Most people know intuitively that if you want something to go into solution faster, mix it, right? You agitate it. That brings more of the solute and solvent into contact quicker. Well, let's look at this logically. The speed of the solution process is governed partially by the size of the particles of the solute. Right? Particularly when you're dealing with a solid going into aqueous solution, like sugar or salt. They'll go into solution faster if the particle size is already smaller. And agitating, right? What does agitation actually do? If you just pour, let's say you have a container of water, and you just, there's your spatula, and you have solid there. If you just dump it in there, it goes to the bottom and sits. Now, where do those 1, 2, 3 steps happen? At the surface. So it's just a big lump. That's going to go slowly. And as these particles go into solution, what happens to the concentration close to that lump if you don't mix it? Concentration increases here, very close to that lump, but it's still very dilute up here. It's not uniform yet. So what you're doing is you're allowing diffusion to be your mixer. And that is a very slow process. So when you mix it, you're bringing more of this solid into contact with the liquid quicker. So you accelerate the process of solution. You can also increase the rate by changing the temperature, usually by increasing the temperature, but not always. And then there's one other one called the common ion effect. If you want to put, let's say we have our solution again, and it's just water. And we're going to put sodium chloride into that solution. Okay? It'll go in solution at a given rate, and its solubility will be a certain amount. But if we have another beaker over here, and you already have, say, potassium chloride already in solution, you've already got some chloride ions in there that are common to sodium chloride. So when you try to put sodium chloride in solution, the effect of these chlorides in here, the common ion, will reduce the solubility of sodium chloride in that solution. You won't get as much sodium chloride in this solution because it's already got some chloride in there. And that is works against solubility. Okay? That's all the common ion means. Is there a common ion in there already? Right? An ion common to the one you want to dissolve. Any questions? While I ramble on? See how we do on time. 9:45. We're good. Okay. There's some general rules that can help us qualitatively predict solubility. The most important one has to do with polarity. When we talk about polarity, I think we've talked about polarity, right?
Did we talk about polarity of bonds? Maybe we didn't. Sometimes I get confused with the other chemistry class. Let me look at basic concepts. Chemical bonding, covalent bond. We did talk a little bit about covalent bonds, polarity of their bonds, I think. But I'll review it. When you have a, say, a compound that's made up of, let's say, we'll use a good example. How about this one? Y'all probably not old enough to remember dry cleaning with carbon tetrachloride. No, it was long gone before y'all came along. Carbon tetrachloride used to be the chemical was preferred chemical for dry cleaning clothes. It was very effective. Carbon tetrachloride. So you had a carbon here, and you had a chlorine here, and a chlorine here, here, and then backwards. So it formed a tetrahedron in shape. Regular shape. These chlorines were regularly spaced around the carbon. And it was a very effective dry cleaning agent. They throw your clothes in this big tub, close it up, and inject the carbon tetrachloride, and it would very effectively dissolve all the grease that it collected in your clothes, oils. Most of the soiling of clothing takes place as greases and oils, like from your skin, or you just pick them up from wherever. And it's difficult to get them out of clothes unless you use soap. And I'll have to talk about how that works later. But this is a very effective grease solvent. And then you wash your clothes in this carbon tetrachloride, and then they remove it. And then when you take the clothes out, carbon tetrachloride is very volatile at room temperature. So all you need is to hang your clothes up or run them through a tumbler with forced air, and the carbon tetrachloride just evaporates. And it's very mild on most fibers. So that's why they use it on very sensitive fabrics, and why it's very expensive. Well, when we could use it, it was very effective, but it's toxic too. So that's why the EPA and OSHA eventually said you can't use that anymore. So you have to use a substitute. So they moved to other types of dry cleaning agents that aren't as effective, but they do the job anyway. Okay, back to my topic. So, how attractive are individual elements on the periodic table to electrons? And that term is known as electronegativity. That is, the higher the number, the more attraction the element has for electrons. And these guys up here in this upper right-hand corner have an extremely high, strong attraction for electrons. But these over here and down here have a very low attraction for electrons. They have low electronegativity. So when you combine something to the left and something to the right in a bond like this, carbon and chlorine, see, carbon's to the left, chlorine's to the right. When you combine those two in a bond, the distribution of electrons between the carbon and the chlorine is not uniform. In other words, more electron density collects over on this side toward the chlorine because it has a stronger attraction. That makes this bond polar. Okay? And we have a symbol that we use, a little arrow like this with an arrow on it and a plus on that end. That's to show you that this is the plus side and this is the negative side. And that's a little Greek letter called delta. It just means we don't have a full negative charge or a full positive charge, like you would have, say, with sodium and chlorine, right? In this case, the electron is completely transferred to chlorine. Sodium doesn't have it anymore, right? But in this case, it's only a slight distribution. So that bond is polar, okay? Now, if you have a molecule that has, say, a polar nature, water is a good example. So if we say oxygen and hydrogen, right? So oxygen is over here, hydrogen's over there. So the distribution of electrons is this direction. Okay? So that means this side is slightly negative and this side is slightly positive. Now that's characteristic of each bond, but what would happen if that's the actual shape of the molecule of water? Two hydrogens this way, like that. What if it was like this? You would still have the bonds like that, but they would be opposite to one another and they cancel each other out. So even though the bonds would be polar, the whole molecule would be non-polar. Okay, I'm going somewhere with this, trust me. But since the molecule is this shape, then I'm going to use a big word, vector summation of these polar bonds is overall that direction. So it's negative on this side, positive on that side. Okay, what does that mean to solubility? Well, if this is polar, if it has a negative and a positive side, and we introduce a solute into water that is also polar, then it's going to orient itself so that the positive side of that other molecule is toward this side of water, and the negative side is away from that side. So over here, you might have another water molecule with the positive side this side, and the negative side that side, and then you would have formation of an attraction there. Okay, that's why we can say like dissolves like in most cases. That is, polar solvents are more likely to dissolve polar solutes. Right? So this molecule, even though each one of these bonds is polar, they're regularly spaced around the tetrahedron, and they cancel one another out. Right? So the bonds might be polar, but the whole molecule is nonpolar. That's why it dissolves grease so well, because grease is nonpolar as well. Greases and oils are nonpolar. So this carbon tetrachloride was very effective at dissolving the oils that were in your clothes. Water was less effective because it's polar. Okay. The substances, solutes and solvents, when their polarities are very similar, are very highly soluble in one another. When their polarities are very different, like nonpolar versus very polar, then you won't get them to dissolve. Perfect example. Any of you make your own salad dressing? No? I do sometimes. You mix, you get some oil, of your whatever kind of oil you like, olive oil is good, and vinegar. And then you find some type of seasoning that you like. When all else fails, I just throw some Mrs. Dash in there. And you mix those two together, along with your seasoning, and then you put it in your little container, whatever it happens to be, and you shake the hell out of it. And it forms an emulsion. That is, it breaks up the oil droplets into very small particles, distributed among the vinegar, but if you set it down on the table, very quickly they separate. They will not dissolve in one another because the vinegar is polar and the oil is nonpolar. They don't like each other. But we like the flavors from either one, so we want to mix them together and put them on our salad. So you mix them up real hard, put it on the salad before it has a chance to separate, and then you eat the salad before they separate. Okay. By the way,
You ever make SOS? No? That's a military term. Shit on a shingle. You make a cream sauce with dried chipped beef. You just cut it up in small pieces and mix it in there. And then you pour it on bread or you pour it on rice. It's pretty good. But they come, the chipped beef is most commonly is made by Armour. It's in these little bottles, about that big around, about that tall. And they've got these press-on caps. And they're vacuum sealed, okay? So when you pull it off, you feel it go shh. But after you get through using it and you clean up those little bottles, they're perfect for making salad dressing. Because they're about that big and this perfect for just one serving. You just mix your stuff up in there and snap the lid back on and just shake it like crazy.
Let's see, where am I headed with this? Like dissolves like. Most cases. So that's why sodium chloride is very soluble in water. Because not only is sodium chloride polar, it goes one step further. It is ionic. And those differences in electric charge cause water to be very strongly attracted to those ions. They go into solution very well. Sugar. Sugar is surrounded by OH bonds. So the molecule is going to be, well, this is glucose. That's hydrogen, hydrogen, oxygen, hydrogen. And then you've got OH is all over the place. See, down, up, down. Right. So wherever you have these OHs, you've got a polar bond there. Right? And these are places where water can be attracted to. Right? So sugar goes into solution. It's very soluble because of all those OH bonds there. Okay. Let's see. Solubility. Okay. Did I give you a? I didn't give you a handout on solubility, did I? If I did, it would have been at the very beginning of the year. Did I incorporate it into the? No.
It solubilities.
Yes.
Salts.
Yeah, there you go. That solubility chart tells you whether or not a certain combination of ions will be soluble in water or insoluble in water. Okay. So in order to use it, all you have to do is say, what's the cation? The cation means the positive ion. It's listed across the top. And you find that one, and then you combine it with an anion, like sodium would be combined with chlorine. And then you look at the negative ion down the side, and you follow them to where they meet in the middle. It's like reading a mileage chart on the map. And if it's gray, the combination is insoluble. If it's clear, then the combination is soluble. Okay? And there's some rules at the bottom. We're going to use the table. You can use the rules to determine solubility, but I would only require those of students that are going to actually be chemistry majors.
then it would be valuable to learn the rules. But for just determining solubility of proposed compounds, it's just as effective to use that chart. And these rules, or this table, is developed from that chart and those rules. So anything from the 1As, where you have lithium, sodium, potassium, any one of these will always be soluble, no matter what anion it's combined with. Ammonium, when it's combined with something, it's always soluble. Acetate, where we said the calcium acetate, the sodium acetate, ammonium acetate, those are all soluble. Any of the nitrates, NO3 minus is one of your polyatomic ions. When it's combined with a cation, it's always soluble. So those are good ones to remember if you need a rule. And then we have other rules that are applicable. So those are the solubility rules. Just for future reference, if you have these rules in a list, they're in this order on purpose. Because you may say, okay, I've got something that's a combination of this and something else. But the one down here says that it's insoluble. Well, if this one says it's insoluble, and you look up here and say one of these above it says it's soluble, the one above it takes precedence. Okay. So the lower the number, the up in the chart, or up in the table here, is the one that wins. Right, so if this one says it's insoluble, but that one says it is, then it's soluble. That's why they're in that order. Oh, there it is. Solubility rules. So we can say, all right, there's sodium, there's chlorine. We already knew it was soluble, didn't we? How about calcium sulfate? It's insoluble. What is calcium sulfate? Well, if you add a couple of waters to it, you get gypsum. They press it together and slap some paper on both sides and stick it up on your wall board. Calcium sulfate. Or if you go in for radiography of any kind, of your GI, you have to drink that nasty solution. It's made of barium sulfate. So it's insoluble. That's why they use barium sulfate, because it won't dissolve and your body won't absorb it. So you can drink the stuff and it helps them visualize your GI tract better with x-rays. But it just passes on through, and it doesn't, your body doesn't absorb it. Plus, barium is down here. It's a big, big atom. So it picks up those x-rays very efficiently. And that's why they use it as a contrast agent. I'd rather drink it. My wife has had the other end, the barium enema. Okay. I hope I never have to do that. Other things. How about silver and chlorine right here? Silver chloride is insoluble. I used to use silver nitrate is soluble. Right? Silver nitrate is soluble. So you put silver nitrate in solution, and there's any chlorine in there, it'll turn to a white precipitate. And you can detect the presence of chlorine with it. Okay, so let's move on. So if you have the greater the difference in your solute-solvent polarity results in less solubility, right? The more similar they are in polarity, the more soluble they are in one another. So which of the following ions are generally soluble in water when combined with lead 2+ ion? Well, you have to look at your chart and say, All right, let's look at lead with sulfide, chloride, nitrate, sulfate. And this is a stupid one, right? Because yeah, go ahead. Because you don't form compounds between, ionic compounds between a positive ion and a positive ion. So E is definitely out. Let's see, do I owe you anything? I don't think I have anything to return, do I? You're going to need, you weren't here last week, were you? You were here? Okay, so you have a copy of Boyle's Law for today? Okay. You also need, did you get a copy of Chapter 8? PowerPoints? I'll bring it to you. Because I want to give you the lab. I want to go ahead and give you the lab for when we come back for it. Next week's work. We're working on Chapter 8 right now. Okay, so if you look at your chart, you find that lead 2+ forms insoluble compound with sulfur, forms an insoluble compound with chloride, and an insoluble compound with sulfate. But it is soluble with nitrate, right? In fact, all nitrates are soluble. But you just have to look at that chart and follow the lead across each one of the ions and see whether the square is grayed out. Let me check something before I proceed any further. Let's see. All right. Yes, I have checked closely. But if the next exam has questions of solubility and you need that chart, I'll give it to you. Either a hard copy or I'll show it up on the board so you'll have access to that chart. So if you have homework questions that require solubility determination, then go back to that chart and use that to help you answer those questions rather than the rules. Of course, if you use that chart often enough, the rules just kind of sink in. You know, it's kind of like naming compounds and doing dimensional analysis. The more you do it, the more familiar it gets, and you automatically memorize all of most of the elements that you're going to use. You memorize them if you use them enough. Okay, now how do we express concentration? We talked about solubility and relative terms such as concentrated, dilute, saturated, unsaturated. Those are qualitative measures. We want to determine concentration in a quantitative fashion. So that means we've got units of measure that tell us how much solute is in the solvent that we possess. Okay. So there are some very common definitions. One is percent concentration. And that just says how many grams of solute are contained in 100 grams of solution. Okay, so if you have 100 grams of solution and you know it's, say, 2%, that means for every 100 grams of solution, you know you have 2 grams of solute. Okay? Or if you have, and this solution can be any kind of solution. It doesn't have to be aqueous. It could be an alloy, right? So with, well, I was talking about gold earlier. With 14 karat gold, 24 is 100%. Let's just do that calculation. 14 divided by 24, oops, back up, that's 100, is 58.3%. Right? So this wetting band is 58.3% gold. Okay, that means it has 58.3 grams of gold per 100 grams of ring. Okay? All right. One that's more commonly used for aqueous solutions is called molarity. And we give it a symbol, a big M. And we can use a big M primarily because there's nothing up there that has a symbol of just one M. They've all got M plus something else. There's magnesium, there's manganese, there's, where's another one? I saw another one a second ago. Molybdenum. MO, there we go. So there's no just one M's up there. So we can use this and not get it confused with one of the elements. But molarity means how many moles, right? That's my abbreviation, my substitute, my symbol for moles. How many moles are in 1 liter of solution? Okay. Now the thing about molarity is it's great because if you know this value, like say you have 1 molar, that means if I have a liter of that solution, I know that I have exactly 1 mole of solute in my possession in that solution. If I take out a tenth of that, say 100 milliliters, right? That's a tenth of a liter. Then I know I have a 10th mole of solute. Okay? Now the formula, of course, is molarity equals the number of moles per volume of solution. And the volume has to be in liters. So that means, since we have a formula, if you know 2 of those, you can find the third. Right? If you know how many moles are in your liter of solution, you can calculate molarity. But if you're given molarity, and you know the volume that you possess, how do you find the moles? Well, you solve for N. Right? Just multiply M times V. Right? This one goes over here. M times V equals the number of moles. So if you know these two, molarity and volume, in liters, then you can calculate the number of moles that you have in that volume. Or if you, let's see, what would be another one? If you want to solve for volume, then you have moles divided by molarity. Right? You swap places, put this one over here and that one over here. So if you know you want a certain number of moles from a solution of a given molarity, then you divide the moles by the molarity, and that tells you how much volume you need to pull out to give you that. Okay? So it's like any formula. If you know 2, if you know all but 1, you can solve for the unknown. Now, the problem with molarity is it's relative to volume of a liquid. So what happens when you change the temperature? The volume of your solvent, and consequently your solution, changes. And if the temperature difference is big enough, the difference in volume is large enough to influence the actual value of M. So if temperature is not an issue,
say you're doing all your work at room temperature, same temperature that you made the solution, and it doesn't change over time, you know, no big deal. But if you're going to do an experiment that requires a change in temperature of 10, 20, 30 degrees, then you're going to run into problems because the volume is going to change during your experiment as the temperature changes. So molarity would not be a good expression of concentration in that type of experiment. Right? So we have a different expression for concentration that is insensitive to temperature. It's called molality. So instead of a big M, we use a little m. And molality is the number of moles, but it's per unit of measure that is insensitive to temperature. It's relative to mass. Mass of the solvent in kilograms. Okay? So this expression of concentration does not vary with temperature, right? Because mass doesn't change when you change the temperature. Moles don't change. Right? So that's what we're going to use for the molar mass by freezing point depression. That's the lab we're going to do when we get back from, let's see, from break. Is it going to be on the day we get back? Yes. The day we get back, on the 5th of April, we're going to do molar mass by freezing point depression. So, oh, you need a break?
Yeah.
Do y'all need a break? we can take a break if you'd like. So that's what we'll do. Assuming we get finished with this chapter today, then we'll have that time prior to the lab that we can discuss how the lab's going to work. Okay? In fact, in this chapter, we're going to talk about freezing point depression. It's otherwise known as a colligative property. I'll define that for you in a few minutes, I think. But the freezing point depression is based upon this concentration, not molarity. Because freezing point involves temperature, right? So if the temperature is going to change during the experiment, we don't want molarity, we want molality. Okay. The problem with percent concentration. We'll go back to that one for a second. The problem with percent is its dimensionless number. Percent means parts per 100 parts, which means it has no dimensions, right? Parts cancel. So percent is a tricky, we have to use it because it's sort of grandfathered in. So when you talk about percent, you need to specify what type of percent is it. Are these units in mass? And these units in mass? So that would be percent, mass, mass. Right? So it would be so many grams per 100 grams. Or is it volume, volume? VV. So it would be like so many milliliters per 100 milliliters. Or a combination. Is it mass, volume? So that would be so many grams per 100 milliliters. This would be milliliters per 100 milliliters. This would be grams per 100 grams. Okay? That's the problem with percent. You got to be specific. And commercial products rarely tell you that difference. For instance, when you go to buy vinegar, you look on the side of the bottle, what does it say? It doesn't even say percent. Well, it does say percent, but it doesn't say the units. It just says 5% acidity. Then you scratch your head. What are they talking about? So I've done some research, and what it means is 5% acidity just means 5 grams of acetic acid per 100 milliliters of solution. But they don't say that on the bottle. You got to dig for it. Okay. So here's percent by mass. This is a very common way of expressing composition. Now, we're talking about solutions here, but I want to digress for a second. When a chemist gets a compound and is expected to characterize the compound based upon its elemental composition, right? So many say we have carbon, hydrogen, oxygen in that compound. So it has so much percent carbon, so much percent hydrogen, so much percent oxygen. It will be expressed in these terms, mass per mass. And the mass would be the mass of the total amount. But we can also use that expression for solutions, right? Mass of solute per mass of solution. Now, what do we mean by that? This is a tricky part. This is easy. Mass of the solute is just, that's it. But the mass of the solution is what? It's a combination of the mass of the solvent plus the mass of any of the solutes that are combined. So the mass of the solution is a combination of solute and solvent. So don't let that throw you. So percent by mass of a solution where we have 5.5 grams of glucose in 78.2 grams of water, we would have to say 5.5 grams plus 78.2 is the solution mass. Well, they're not going to show us. So the percent glucose is equal to 5.5 grams of glucose. And then the mass of the solution is 5.5 plus 78.2 times 100. So you have to add those two together. By volume, so we have 30 mils of methyl alcohol in 435 milliliters of solution. See, they gave it to you here. So if you add enough water to make this much solution, you've already got the volume of the solution. You don't have to add the volume of methyl alcohol to it. Besides, it wouldn't work anyway. For one reason. When you add, this happens very often when you add two liquids together. 30 milliliters of methyl alcohol and say 405 milliliters of water. So if we have 30 milliliters of methanol plus 405 milliliters of water, what volume will that give you? Would it be 435 milliliters? Nope. Why? Because this methanol fits into spaces in the water, right? So it's actually less than 435 if you base it on these two volumes. So the total volume is less of the solution. So that's why they say add enough water to give you a final solution of 435 milliliters. So it will probably take more water than 405, maybe 410, 415, to give you a final volume. Now with mass, you got what you got. But with volume, you got holes in there for the solute to fit in. That's why when we make a solution based on molarity, we use volumetric glassware. You may have seen this stuff. It's got a long neck and a big bulb at the bottom, and it's got a mark on here, usually etched, scribed into the glass. So let's say this flask is designed to hold exactly 1 liter. They come in different sizes, but for argument's sake, let's say it's 1 liter. That's what this mark means right here. That's the 1 liter mark. So if you have filled that up to that mark, you're guaranteed to have 1 liter of solution. Right? So that way, you don't have to depend on adding liquids together and knowing what their volume is. Right? You add your solute in there, maybe it's a solid, and then you fill it up with enough water, say, to dissolve it, get it in solution, and then you fill it up to the mark with your water. Now, when you have water in glassware, the convention, how you read the position of that water in the tube, and water behaves this way in glassware. So if you have a long tube and you have water in there, it forms a meniscus like that, curves down. Okay, so you read it, it's designed to be read at the bottom of that meniscus. Okay, any type of glassware with aqueous solutions, you read at the bottom of the meniscus. And then you have 1 liter, and it's also calibrated at a certain temperature, usually 20 degrees, right? Because when you're dealing with volume, temperature is important. Now, what if, remember we talked about solutions that get hot or cold when you mix them up? What if this solution gets hot when you mix those two together? What's that going to do to the volume of the solution? Expand it, right? So if it's calibrated at 20 degrees and it heats up to maybe 35 or 40 degrees, you want to mix it together and maybe fill it up to here and then let it sit for a while. After it's in solution, let it sit, equilibrate with room temperature, then fill it the rest of the way. Then you won't have temperature error. If I knew the solution was hot, I have mixed up those solutions and brought them right up to the mark when they were hot. And then I let it sit. And it's just for fun. And over time, you watch that level drop as the solution cools. Once it gets to room temperature, then I finish filling it up and mix it. And you're ready to go. Okay, what would be the volume percent for this one? Well, you're told what the final solution is, 435 milliliters. So that's the volume of the solution. And the volume of the solute is 30 milliliters times 100 because it's percent. So that's 6.9%. And since this is alcohol, this is ethanol actually, the drinking kind, you'll see it listed on the side of the bottle as ABV, alcohol by volume, 6.9%. That's about like beer. Something like that. Maybe a little less. For wines, it can range between 11 and 15, 16%, something like that.
Middle layer of the bag.
Yeah. And then for distilled liquors, it can be 50%, maybe higher. But for distilled liquors, they use a different method. They call it proof. So proof is 100% is equal to 200 proof. So 50% ABV would be 100 proof. Okay. That's pretty high, actually. My wife and I went to Jamaica for our honeymoon, and we won one of their contests at the resort. We won this bottle of, let's see, what do they have down there? Rum. It's a bottle of rum. Very high concentration, high quality. They wouldn't let us take it on the plane because it was flammable. So we had to leave it behind. We probably could have packed it in our luggage if we'd have known, but we didn't know. Okay, mass volume. It's just a combination of the mass of the solute and the volume of the solution. Okay. So we do it the same way. You have to have some way to know what the volume of the solution is after the solution is made. Right? Because it's going to have those little holes in there, so you can put salt in it, and the salt may not change the volume, but just a fraction. Right? So you can't. Plus, solids, they basically, compared to the large amount of solvents you use, the volume of the solute is negligible. Okay, conversion factors. Once you know the concentration, you can use it as a conversion factor. Right? So if you have something like 15% mass sodium chloride solution, then it just depends on whether you want to convert the mass of the solution to mass of the solute, in which case you need to know 100 grams of solution contains how many grams of solute. And then that part cancels and you get the mass of your solute. So you use it, anytime you have a ratio like this, you can use it as a conversion factor. Because what does that say? That says, for the conversion factor purposes, this is equal to that. Right? All conversion factors are equal to 1. Numerator is equal to the denominator. So any of these concentration values, as long as you know what the units are, you can use them as conversion factors if you need them. Okay. So, okay, how many grams of sodium chloride are needed to prepare 150 milliliters of a 0.9% mass volume sodium chloride? So let's see, what does that mean? Mass volume. That means 0.9 grams sodium chloride per 100 milliliters of solution. That's what that means. So, if we want to make 150 milliliters of solution, then we would multiply that by 150 milliliters. That cancels the milliliters, and 150 times 0.9 gives us the mass of sodium chloride that is required. Right, whatever that happens to be.
150 times 0.9.
135. So that's what you need, 135 grams of sodium chloride in a final volume of 150 milliliters. Gives you that concentration. And you can check yourself. You say, okay, what would it be? Well, take 135 grams and divide by 150 milliliters, a final solution, times 100, and you should get 0.9%. Okay? It's just to check yourself. Wait a minute, did I say 1.35 grams? Oh. I forgot to divide by 100, didn't I? And you just let me ramble on. Right. I just multiplied these two together. Got divided by 100. So 1.35 grams in 150. Yeah, that makes a whole lot more sense. Actually, these calculations are good to do. They're exercises. But familiarity with molarity is much more important, particularly if you're going to be, let's see, medical profession or MLT? Medical? Okay. MLTs? MLT? Okay. So molarity is more important. It's more useful in your daily operations. So that's the one you probably want to focus on, mastering. Moles per liter. So if you have 1 mole of sugar, I assume table sugar, in 125 milliliters, okay, you can't just divide moles by milliliters because that's not the right units. So you have to change milliliters to liters, which would be 0.125 liters. Then that would give you molarity. 8 molar in this case. So if you have 10 molar of a sugar solution, we had 8 molar before, but say we have a little more concentrated. 10 molar, what volume of the solution do you need to have in your possession 2 moles of sugar? Right. So you go back to your definition, molarity equals moles divided by volume. You want to know what volume of the solution you need. So we're going to solve for volume. Volume equals moles divided by molarity. So we have molarity on the bottom and moles on top. We want 2 moles, right? So that's equal to 1/5 or 0.2 liters. Oh, I got some animation for this one. There you go. Wait a minute, 10 liters? That's an error. That is that's supposed to be. That should be. Okay. That should be that. Okay, I assume, since this is molarity concentration, that they want us to find out the molarity of each one of these. So how would you do that? You don't have the right units of measure, do you? You've got masses, 100 grams of each. So how would you find the moles of each? $100 grams of sodium hydroxide. To convert grams to moles, you need molar mass, right? Sodium is 23. Yeah. So sodium would be 23. Oxygen is 16. Hydrogen is 101. So you have 7, 10, 40. 40.01. Divide that into that. That gives you the number of moles of sodium hydroxide. Then you take the moles and stick it in your formula for molarity. Okay. Well, you also have to convert this to liters, right? So paying attention to units is extremely important. Not just extremely important. It's a matter of survival. If you don't pay attention to your units, you won't survive an exam. So here's the conversion, 39.9, okay, close enough. That converts sodium hydroxide to moles, and then moles divided by, let's see, moles divided by liters. That's right. That gives you moles. So this would be 100 divided by 40 on top, and then volume would be 0.250 liters. I think that works. But it turns out it's 10 molar for sodium hydroxide. But will it be the same for potassium chloride? Probably not, because potassium chloride should be a different molar mass. So you might have the same mass, but you have different moles. And for potassium chloride, the same mass dissolved in that volume only gives you 5 molar. Okay. So how do we do dilutions? This is good to know, especially for MLTs. Well, it's useful. It's not so much anymore because medical profession and even medical lab techs, everything comes pre-diluted, doesn't it? And you just use the right bottle of stuff in the machine and do your thing, right? But this is why it works. Right? It used to be nurses had to prepare solutions before they administered them to patients. And every once in a while, they'd make a mistake and make somebody sick or even kill somebody because they got the wrong concentration. Right? So you think you've got a 0.01 molar KCl solution that you're injecting into your patient along with something else. But you make a mistake and you're actually injecting a 1 molar solution of KCl. What happens? The heart stops. Right? That's one of the solutions that they administer to death row inmates. KCl stops their heart like that. Anyway, how do we do dilutions? Well, I think this is the way the book gives it to you. But if you look at it this way, I'm going to draw you a picture. If I got time, let me see. Coming up on, am I out of time? 11:15. Okay. Okay, we're good. Just wanted to be sure. Boyle's Law Lab doesn't take a lot of time, so we're good. we can give you this formula. Concentration of the stock times the volume of the stock equals the concentration of the diluted times the volume of the diluted. Or I like to write it M1V1 equals M2V2. This is why it works. Okay? So the dilution process goes from more concentrated to less concentrated. When I was working in soils, we would do extractions of soil with certain types of solutions. And then we would analyze the solution for its elemental content and make some predictions about how healthy the soil is for certain crops. But we didn't want to have to make out these dilute solutions every time from scratch, like adding the solids into the solution. So we'd make up concentrated jugs, concentrated, and we would take those and dilute them to the desired concentration when it was time to use them. So here's our concentrated, and here's our diluted solution. Okay? We're going to take a portion of this one and put it into a greater volume of solvent. Okay? So when we take that out of there, how many moles do we have? That's the first question. Well, we know the concentration is that molarity, right? So if we say molarity equals moles per volume, then if we take out a certain volume and we want to know how many moles we have, molarity times volume equals the number of moles. Okay? So for this one, the number of moles that we take out of there, we just need to know the molarity and how much volume we take out. And that's the number of moles. So we put it over here. Has the number of moles changed? Same moles, right? So over here, we have a different concentration because we've added more solvent. And over here, the number of moles that we now have, we're putting this number of moles into fresh solvent with no other moles in it. So we've only got the moles that we brought over. So that number of moles is equal to the moles that are over here. So that means N2 equals this concentration times the total volume here. Right? Over here, the V1 is that little bit of volume that we brought out. So if this is equal to that, this is, what do they call it, the distributed property, and that's equal to that, then that has to be equal to that. Right? That's why M1V1 equals M2V2. You just have to remember which one's which. Right? I always make M1V1 the concentrated one, and M2V2 the diluted one. Oh, we're going to use their terminology. Okay, so if the concentrated one is 10%, and we want to end up with 0.9% rather than 10 in a total volume of 100 milliliters, then we have an equation in one unknown, and we can say this is how much of the concentrated solution that we need to put in 100 milliliters to give us that concentration. So that's how dilution works. Let's see. A 0.5 molar solution of sodium chloride sits on a lab bench. Which of the following would decrease the concentration of the salt solution? Add water to the solution? Yep, that'll do it. Decrease the concentration by adding more solid. Pour some of the solution down the sink. Does that change its concentration? No. Changes the total volume, but not the concentration. Add more sodium chloride to the solution. That would increase the concentration. Let the solution sit out in the open air for a couple of days. Water would evaporate, would increase the concentration because you're losing solvent. So really, that's the only one that would decrease the concentration. Add more solvent. What's the minimum volume of a 2 molar sodium hydroxide solution needed to make 150 mils of 0.8 molar sodium hydroxide? Okay, so what I like to do is say, especially with these word problems, set up my chart on one side and pick the information out of the problem so that I don't put it in the wrong place in my formula. Put it in the wrong place in your formula, you get the wrong answer, of course. So what's the minimum volume of this concentrated sodium hydroxide solution that you need to make the Molar solution? So the concentrated is 2 molar, and this is unknown, and you want to end up with a molarity of 0.8 and 150 milliliters of solution. Okay, so there's your information. And if we have M1 V1 equals M2 V2, do we need to change this to liters? Yes, no, maybe? No, you don't. Why? Because the volume that you put in here is going to be the same volume you get out there. Why? Because if you write it this way, put that one over here, then put this one over here, what happens? Well, if this is liters, they cancel. If this is milliliters, they also cancel. So the units of measure don't matter. Now, if you're using the formula MV equals N, number of moles, yes, you do have to have the correct units there. But when you set up a ratio like this, you can use milliliters just as easily as liters. So we put in our values. M1 is 2. Volume is unknown. M2 is 0.8. And 150 milliliters. The beauty of that is, when you get your answer for volume, it's going to be in milliliters already. And it should be 60 milliliters. So what does that say? That means if you take 60 milliliters of this concentrated solution and dilute it with extra water until you get 150 milliliters final volume, its concentration will be 0.8 molar. Okay. All right, we must be getting close to the end. Color? No, not quite. We still have time. Let's see if we can manage. So what's a colloid? Well, this is sort of a, colloids are real. Let's just put it that way. They're real, but they're not solutions. They are, in some respects, homogeneous mixtures because the particle sizes are small enough so that they stay suspended in such a way that the concentration is the same everywhere in that mixture, right? So while we may call them homogeneous mixtures, they're not really. Well, qualify that. They are homogeneous mixtures. They're not solutions. There is a dispersed phase that we would call the solute in a solution, and a dispersing medium that we would call the solvent. Now, it's all based on particle size. If you make the particles small enough for the solute, they will stay suspended. Small enough for the dispersed phase, they will stay suspended in the dispersing medium indefinitely. Okay? Example, Jello. Jello is not a solution, it's a colloid. Now, how do you tell a colloid from a solution? Easy. Look for the Tyndall effect. Right? You just take a jar, a transparent jar, of what you think might be a solution, shine a light through it. If you can see the light beam in your medium, it's not a solution. If it stays suspended indefinitely, it's a colloid. Okay, that's the test. Why do you see the light beam? Because those particles are independent from the dispersing medium. And when the light shines through there, it bounces off those particles and you can see the beam. Whereas in a solution, those particles are intimately dispersed in the solvent and they behave exactly like the solvent. So when the beam goes through, it doesn't strike anything different as it goes through. It just thinks everything's the same, goes right on through, you don't see it until it gets out the other side. Oh, there's the Tyndall effect. I don't know if I have a picture. Yeah, there we go. This is extreme, right? The light beam passing through a solution, you know, you can't see the beam. But once it hits over here, you can see it right there. Right? That's the Tyndall effect. This is a colloid. That's a solution. Now, colloids don't have to be a dispersing medium of a liquid. You can have gas, you can have solids in gas colloids. In California, they call it smog. A suspension is a heterogeneous mixture. That's definitely true. But a suspension is unlike a colloid in that if you let it sit long enough, the dispersed particles will settle out. If they're heavier than, they're denser than the dispersing medium, they will settle to the bottom. Of course, if they're lighter than the dispersing medium, they'll float to the top. But they are affected independently based on gravity as the force to pull them apart. Let's see, what do we have here? Solution, colloid, suspension. Okay. Solution's a homogeneous mixture. For argument's sake, colloid is a homogeneous mixture. It's just that the types of particles you get here are atoms, ions, and small molecules. Whereas with a colloid, you have particles, but they're generally larger molecules. They don't go into solution. And they don't have to be the same polarity either. Okay. Colligative properties. Okay, I think this is the last topic. This is where we cover a topic that you'll need for the lab when we come back from spring break. So what do we mean by colligative? A colligative property is physical. It's not chemical. So you're probably wondering, why do we need it in chemistry? Well, chemistry is supposed to be the central science, so it draws from all directions. But physical properties are useful in chemistry. In fact, we're going to use physical properties, one colligative property, to determine the molar mass of a fatty acid. Okay. That's what we're going to do with our freezing point depression experiment. A colligative property is one that depends entirely on the number of solute particles in the solvent. It doesn't matter what they are. It only depends on the number of them. Right? So that's convenient. Right? If you don't know what your solute particles are when you start, then you can gain some information about them using a colligative property, right? Such as molar mass. If you know the molar mass of your molecule, combine that with some other information, and you might be able to tell exactly what it is. So colligative properties are very useful. These are the four most common. Vapor pressure, lowering the vapor pressure of a solution based on how many particles of solute you have in the solution. Right. We're not going to use that one. Boiling point elevation, that is, if you add solute to your solvent, it will increase the boiling point. So that's why salt water boils at a higher temperature than fresh water. Or freezing point depression, that's the one we're going to use. So the freezing point of water decreases as you add salt to it. That's why we add salt on our roads. It dissolves in the thin layer of water that's on the surface of the ice, and then it won't refreeze. And then as ice naturally goes through cycles, like freeze, thaw, freeze, thaw, freeze, thaw, at the microscopic level. So when it does, that salt is there to dissolve in the water. It won't let it refreeze. So eventually it works its way down and all the ice is dissolved, melted. Its freezing point is depressed. Its freezing point now is lower than 32 degrees Fahrenheit or 0 degrees centigrade. And that's good because it can get colder and colder and colder and the ice won't stay. Snow won't stick. And the other is osmotic pressure. So we have to define what these are for them to mean something. Let's see, if you had A&P, anatomy and physiology, if you had that, maybe, or maybe a biology class, they probably talk about osmotic pressure. So how is the vapor pressure lowered? Well, to make a long story short, if you have a lid on your liquid, then some of that liquid, when you first put it in there, is going to evaporate. It's going into that headspace and start building pressure because you've got it capped. But as you get more and more of these, say, water molecules up here in this, then you get a reverse. So you get some going out, some going in. At some point, you reach an equilibrium where the rates of vaporization and condensation are equal. Then you establish a vapor pressure. That's the pure vapor pressure of the solvent. Now, what happens if you add some solute to that? Like salt. Well, you've got that everywhere in your solution, so the surface has some of it. So that decreases the amount that leaves the surface because some of it is salt and it's not volatile. Right? So you decrease the vapor pressure because there's not as much of your solvent at the surface. And this is the expression. So the vapor pressure of the solution is equal to this value of the solvent times the vapor pressure of the pure solvent. So the pure water here would give you a certain vapor pressure. And if you know this X value, which will be a fraction less than 1, then you can calculate what its true vapor pressure is. This X value is called the mole fraction. So that just means in a sample, how many moles of solvent are there relative to the total moles of the solution. So that's why it's a fraction less than 1. Okay. Boiling point elevation. Let's go from this one. Let's go to the one that we're going to be using, because the form is the same. So you have a change in temperature, boiling point elevation. So it'd be an increase of delta T up. Is you need to know the molality, moles per kilogram of solvent, because we're talking about temperature. So we want something here, an expression of concentration that doesn't respond to temperature. That's why we use molality. And then this value is characteristic of the solvent. And it's different for every solvent. You have to be given that value. For water, it's this, 0.51 degrees centigrade for every molality. So since we're going to be using
Benzoic acid dissolved in lauric acid. I think that's right. Then we need to know lauric acid is the solvent, so we need to be given a value, which is in your method,
corresponding to the K for lauric acid. Right. Then we can use that formula for lauric acid. So that just means that delta T, or the change in temperature here, and this is an absolute value. So if it's a negative, well, that's boiling point elevation. It's a freezing point depression. So if the temperature decreases, you get a negative delta T. It doesn't matter if it's negative or positive. You take the absolute value. You just want the number, the change. And that's equal to this K value, or freezing point depression, times the molality of your solute. Right? So this is going to be in units of mole per kilogram solvent. Okay? And this is going to be in units of degrees C per molal. So if this is molal, it cancels this one and leaves you with degrees C. Okay. So it's real simple. Okay. What if we add a non-volatile solute to a solvent? What does it do to the vapor pressure? If you add a solute, you're going to decrease the vapor pressure. Okay, osmosis. I think this is the last topic. So what is osmosis? Well, for our purposes in living systems, we're talking about the movement of water. So the movement of water across a membrane. And that membrane has to be semi-permeable. That is, it only allows water or smaller molecules through. So it might let gases through too, like oxygen or carbon dioxide. And that's what happens in cells. When cells are metabolizing, oxygen goes in, from the capillaries. It diffuses across the capillaries into the cells, and they use the oxygen to metabolize their glucose primarily, and they get energy from it. But they also produce carbon dioxide. Well, that carbon dioxide diffuses back out through that membrane. Gases go in and out with no problem at all. Water will also move in and out of the membrane, through the membrane. So the question is, how do you know which direction the water is going to move? All right. Well, if you have a cell, right, it's got lots of stuff in it. and it's also got water as the solvent. Right? So it's at a certain concentration. If you think of the concentration in terms of water and not this other stuff, it might help you understand which way the water is going to move. So if you put that cell in a container of pure water, which way is the water going to move? It's going to move in the direction toward the direction where it's lowest in concentration. Right? It's going to move from big to small. So it goes this way. Okay. And if it keeps going, the cell will rupture. So that's what happens. I saw this little video. A high school teacher was going to show his kids blood cells, his own blood cells under a microscope. Right? So he pricked his finger, and smeared it on a slide, and then he knew it was going to dry out, so he better put some water on it. So he got some distilled water and put it on there, and then put a little cover slip on it, stuck it under the microscope, and there's nothing there. He put distilled water on a blood cell, and just that quick, water moved into the blood cell, poof, blew them all up. Got no cells left. So what do you need to do? You need to immerse the cell in a solution that's the same concentration of water outside as inside. So that means you need more of these other solutes out here to give you the same concentration inside and out. Then the water won't move. Okay, that's called an isotonic solution. Okay. Now, what are the other possibilities? Well, the solution outside the cell, if it's pure water, is hypotonic. If the solution of water is low and you have lots of solute in here, more than is in the cell, is hypertonic. So if it's hypotonic, water is going to move into the cell, and if it's hypertonic, water is going to move out of the cell. And the blood cells would, what do they call it, crenulate. They get crinkly, right, because you're sucking water out of the cell. Water is moving in the direction where it is less concentrated. Now, what do we mean by osmotic pressure? Well, the cell experienced that osmotic pressure when water moved into it, right, and exploded. But up until the time when the integrity of the membrane was exceeded, there was building pressure inside the cell. That's osmotic pressure. How do we measure that? Well, to measure it, we need to be able to put the membrane, in this case, on a tube, and the concentrated solution is inside the tube, and the less concentrated is outside. So the water is going to move through that membrane in here, and gradually dilute that solution in there and increase its volume. Okay? So it reaches a point where the concentration of the pressure here is forcing water back at the same rate as it is coming in. When it reaches that equilibrium point, then the difference in this surface and that surface is a measure of the osmotic pressure. Okay? Let's see. That doesn't tell us anything new. Now, here's an interesting concept. What if we have a concentrated solution in here and a dilute solution out here? If we let it go of its own accord, water's going to move through that membrane and actually build this up in pressure until it reaches equilibrium. But what if we can build pressure on this side of the membrane? If we can counteract the osmotic pressure sufficiently, we can drive the water backwards, and the water would come out through the membrane that direction, because we exceed the osmotic pressure of that solution. That's called reverse osmosis. And that's one of the technologies that is being used in many places around the world to desalinate water. Right? If you have a large amount, if you have lots of salt water, but not fresh water, then if you build pressure against that salt water and a semi-permeable membrane, then you can drive the water out through the membrane and leave behind a brine. And out here, you have pure water. We used to use reverse osmosis in the laboratory to simulate, actually, distillation. So we'd have pure water from our reverse osmosis setup, relatively pure, and we could run it through some other cleaners, but it was a good start to make relatively pure water by reverse osmosis. Okay, see how we're doing. We're a little over, so let me see. What do I need to do? I've already described isotonic and hypotonic. Yeah, so we won't have to spend a lot of time on that. But this is interesting. I used to wonder, I knew about these trees out in California, the sequoias. They're like 300, 350 feet tall. And I said, how in the world can that tree get water from the ground and send it all the way to the top? Well, okay, if you have a bowl of water, and you have a long tube, like that, there, and you pull a vacuum on that tube, how high will the water go? Well, it depends on the atmospheric pressure. So at sea level, you've got 1 atmosphere pushing on this, and the difference in pressure is between what's inside and what's outside. So if you pull a vacuum, then all of the pressure here is forcing water up. Right? How high will it go? "33 feet. That's it. You can't get it any higher with a vacuum. Okay? So it can't be that. You can't be pulling a vacuum above the water in this tree and expect it to go 300 feet. It won't happen. So it's not a pull, it must be a push. So what would supply the push sufficient to get water to climb 300 feet in a sequoia? Well, it's not just a simple tube. A tree root and all of the xylem in the tree, which is the water conducting tissue, has dissolved solids in it, dissolved substances, which in contact with fresh water in the ground will sit up in the osmotic pressure, right? So the tree in its roots has a higher concentration of solutes in its cells than the groundwater outside, right? So which way is the water going to move? It's going to go into the tree. And if you can set up a difference in concentration between outside the root and inside the root, sufficient pressure inside there, then you might be able to drive that water all the way to the top of the tree. It's been measured. The osmotic pressure in the roots can exceed 20 atmospheres, right? So if 1 atmosphere will go 33 feet. How far could 20 atmospheres possibly go? Well, 10 atmospheres would be enough, right? It would send it 330 feet. But 20 atmospheres, that tree could conceivably be over 600 feet tall and still get water to its top. So osmosis is the answer. Osmotic pressure developed in the roots of the tree is sufficient to drive water to the top of the sequoia. Now you got something to amaze your friends at parties. Or a trivial pursuit or whatever. All right, there's another term, osmolarity. Molarity we know is moles per liter. But osmolarity takes into account the effect of what happens to the solute when it goes into solution. Right? So if we have a 1 molar solution of sodium chloride, what does it do in solution? It splits. So now you have 2 particles for every 1 you put in. So the osmolarity, if you say the molarity of sodium chloride is 1, the osmolarity is going to be 2 because it splits into 2 separate particles. And remember, this is a colligative property. It doesn't matter that it's sodium chloride. It only matters how many particles you have. So if you start off with 1 particle of sodium chloride, you get 2 particles of ions, then your osmolarity is twice. And that's what this I means. Molarity times I is osmolarity. And I just means how many particles. So if we say sodium chloride in solution, the I value equals 2. What if we have, let's see, calcium chloride? What's the I value? 3. 1, 2, 3. Okay? That's why these ice melting prills that you can buy in the store, it's like that superheat they may call them, why they work better than sodium chloride, because they've got calcium chloride in them. So for the same number of moles of calcium chloride or sodium chloride, you get 50% better ice melting ability because you have more particles. The other advantage, of course, is that calcium chloride doesn't eat up your concrete. Have you ever put sodium chloride in your concrete in the winter to melt the salt? You know better, don't you? Because come spring, you're going to have little potholes in your concrete. Sodium chloride is very corrosive to concrete. Calcium chloride is not. I had to learn that the hard way. So I was out in the spring patching holes in my concrete. Okay, so the osmolarity of 3 molar sodium chloride solution is actually 6 molar. 6 osmol. Okay, we talked about hypotonic, hypertonic, isotonic. If the hypotonic solution will produce a lower osmotic pressure than that is within cells, which means it doesn't produce pressure in the cell, it produces pressure to get out of the cell. So a hypotonic solution will draw water out of the cell, and blood cells, for example, will crinkle because they're losing water. And if you wash a lot of dishes in fresh water, your skin will get crinkly too. If you do it by hand anymore, I don't think most people. Anybody not have a dishwasher? You don't have a dishwasher?
But I don't always like.
Oh, yeah, you need a load, right? So if you only have a couple of dishes, right, you do it by hand. So do you do enough of them for your hands to wrinkle?
Oh, yeah, because I have a whole bunch of people in my house right now. So.
Okay.
Dishwasher's full all the time.
So you got your hands submerged in a hypotonic solution. It's drawing water out of your cells and your skin wrinkles. So, wait a minute. I'm sorry, that's the wrong direction. Hypertonic draws water out of your cells. Hypotonic sends water into your cells. Right, because the hypotonic solution has a higher concentration of water outside, lower concentration of solutes outside. It goes into the cell. Okay, so why does your skin wrinkle? Soap. That's the only thing that makes sense, because fresh water should send water into your cells. Yeah. So for a hypertonic solution, you get water moving out of the cells. And the isotonic is ideal for your patients. Inject them with an isotonic solution is safer than either of the other two. Now, sometimes I've talked to EMTs and emergency ER nurses that sometimes you need to inject a hypotonic solution. If your patient is extremely dehydrated, you want to get water into the cells. So a hypotonic solution will do that. But you got to know what you're doing, because you don't want to rupture all their blood cells. You got to do it at a defined rate. Or if you've got a patient that's in congestive heart failure, they might inject hypertonic solution to draw the water away from that sac around the heart, the pericardium, because congestive heart failure will put pressure on the heart. That's not the only reason that you've got congestive heart failure. The heart muscle is just too weak. It can't push the blood, right? So there are a number of factors. So don't quote me to a physician. They'll probably say your instructor's an idiot. Okay. Oh, okay. So isotonic solution. What is an isotonic solution? Well, traditionally, 5% mass per volume of glucose is considered isotonic. And that would be listed as a D5W, or dextrose 5% by weight. Okay. So you might see the bag might be labeled D5W. That's what it means. And that translates into 0.2775 osmol. Okay. I was always told that sodium chloride solution of 0.9% would be isotonic. That's pretty close. The problem with sodium chloride solutions, if you inject 0.9% or drip 0.9% sodium chloride solution into a patient, it might be okay for the short term, but for the long term, you're going to stress their kidneys, right? Because the amount of sodium is not particularly damaging, but you're hitting their system with a huge slug of chloride that they don't need. So that's why lots of isotonic solutions are not entirely made from sodium chloride. They're made from things that you have, what do they call it? Lactated ringer solution. Right? So it's a combination of things so that you won't overstress the kidneys. Let's see. Here we go. If you want to read more about it, go to this article right here, and it talks about overstressing the patient's kidneys with an excessive slug of chloride. So there are physiological reasons not to use 0.9% sodium chloride in your drip. Okay. I think what we'll do is let that go for now and pick it up when you've had a chance to look at some homework problems, and then we can work through some problems. Okay, so let's maybe, what, 10-minute break, and then we'll go in the lab, and we've got a small enough group we can all do it at once. Just do one test
together. Using Boyle's law. So let me stop this and it'll